Chapter 3 Inference for Models with Unobsevables. In this video, there are 6 outlines. First, we will discuss about introductions. Second, the likelihood inference for random effects, extended likelihood principle. 4. Laplace approximations for the integrals. 5. Street magicians. And 6. X likelihood and empirical bias. To begin with the introductions, the X likelihood method can fit rather complex models in an elegant manner. In contrast, classical likelihood software may not be as flexible, whereas Bayesian MCMC or Monte Carlo approaches allow fitting these models but at the expense of more computation time and requires to assign priors for fixed parameters. Therefore, in this chapter, we define the X likelihood and provide insight to inference and predictions based on the X likelihood. We introduce the extended likelihood principle underlying the X likelihood framework and show how it is related both to classical likelihood and Bayesian inference. But first of all, you have to know the 5 important points are made. First, the inference about random effect can be made using the X likelihood, whilst the classical likelihood cannot give any information about the random effects. The X likelihood inference of random effects takes into account the uncertainty in estimating the fixed effects, whereas the empirical bias estimations of the random effects. Whereas empirical bias estimations of random effects assumes known values of the fixed effects. The model checking is possible for all parts of the model, and all necessary inferential tools can be derived from the X likelihood, and the X likelihood can be used for the predictions of unobserved random variables such as future outcomes, and can be used in wide applications within the medicines, engineering, and also social science. This is the example for predictions of future outcome. But suppose that we have the number of epileptic seizures in an individual for 5 weeks. Suppose the Y 32504. This is our Y. And suppose also that these counts are independent identical distributions from a Poisson distributions with mean theta. Here, theta hat 3 plus 2 plus 5 plus 0 plus 4. Summarize and divide by 5. And we can get that 2.8 is the maximum likelihood estimator for our theta. In line with this, to maximizing the features likelihood denoted by f theta y, the inference about theta can be made by using the likelihood. Now, we want to have a predictive probability functions for the seizures counts for the next week v. Then, because our f theta v equals to I with condition y, f theta v equals to I. The plug-in techniques gives the predictive distributions for the seizures count v of the next week by following these questions. To begin with, persons in 1920 point out the limitations of the features likelihood using the plug-in method because it cannot account for the uncertainty in estimating theta. This plug-in technique is a kind of the empirical bias method with Jeffreys prior. So this is the Jeffreys priors, and the resulting marginal priors like this. Gives a predictive probability with the higher probabilities for ledger y. This Bayesian handles uncertainty caused by estimating theta, because we want to estimating theta here. However, it depends upon the choice of a prior, and it might be difficult to justify why the choice of Jeffreys prior is the right choice. To give an example, here the X likelihood including phi is the proportional to f theta 32504 phi and we do the exponential. Now, our theta phi following by 3 plus 2 plus 5 plus 0 plus 4 plus phi divided by 6 because we have 6 variables here is the potential maximum likelihood estimate if phi is observed. Then, the normalized profile likelihoods following by f theta hat phi, this is our profile likelihood, gives the predictive probability p with phi condition y almost identical to the persons but without assuming a prior on theta, following by figure 1. These figures illustrate the predictive density of number of scissors counts, plug-in methods, Bayes triangles. This is the Bayesian methods and the likelihood method, symbolized by plus. This is a method to eliminate theta from the predictive probability f theta v with conditions y. This example shows that standard methods for likelihood inference can be used for the predictions problem by using the x likelihood without assuming a prior on theta. Next, likelihood inference for random effect. But first, we consider the extended statistical models that consist of 3 types of object: data y, parameter fixed unknowns theta, and unobsevables random unknowns, denoted by phi. The statistical inference needs to be made for both unknowns theta and phi, based upon the observed data y. Consider a linear mixed model for E equals to 1 until m and G 1 until ni. So this is our linear mixed models, which is yij equals to xij beta plus vi plus eij. And beta here is the factor of the fixed fx, and vi following the normal distributions, which is the parameter 0 and lambda. Vi should be IID random effects, and eij follows the normal distributions with the 0 and c, is an IID random error. In this model, there are 2 types of unknowns. First, fixed unknowns denoted by theta, and random unknowns denoted by phi. And the theta including the beta, c, and lambda. Therefore, V is the V1 until Vm transpose. The linear mixed model equations 1 in previous slide may be written in the matrix form as in equations 2, which is this is the matrix form from the linear mixed model. In the classical likelihood settings for the model for data generation process f theta y is given by density functions of multivariate normal distributions. Therefore, this one is the normal distribution functions with the corresponding marginal likelihood. So equation 3 defined as marginal likelihood, where V is the double Z transpose lambda plus metric identity with the C. This marginal likelihood can be used to estimate and make inference about the fixed parameters beta, lambda, and C. However, the random effects V is not included, so that the classical likelihood doesn't directly give inference about the random effects. To tackle that issue, Lee and Nader in 1996 proposed the use of the hierarchical likelihood by following in equations 4, where f theta vy in the equations 4 is the joint density of the phi and y. It is related to the conditional distributions of phi given y as in equations 5. Nevertheless, Yon starts introduced the extended likelihood principle where all informations in the observed data for parameter theta and unobservables v are in the extended likelihood, such as the hierarchical likelihood. At the same time, Lee and Nelder in 1996 found that the scale of v is important for meaningful statistical inference. They called the extended likelihood in a particle scale and the hierarchical likelihood in particular scale. Hierarchical likelihood and its logarithm is referred to as the x likelihood. For the x likelihoods, there is a close connection both to classical frequency inference and Bayesian inference. In the absence of random effect, the hierarchical likelihood is the same as the classical likelihood. The x equals to f theta y. So x here is the hierarchical likelihood in the absence of fixed parameters theta. By following in equation 6, which is the proportional to the posterior functions v with conditions y used for inference in Bayesian statistics, where function v is a prior. So our function v, this equation 6, is a prior. However, in the hierarchical models, such as linear mixed models, v is random and our function v is part of the model. To make distinctions clear, we call our functions v with conditions y the predictive density, or we call it predictive probability for random effect v. Following this book, the conditional likelihood f theta v with conditions y the predictive density for random effect v. Lee and Nader in 1996 proposed the random effect could be estimated by finding the mode of the joint density functions of theta, y, and phi. By using the mode of h, can simplify the computations drastically compared to MC-MC. However, it requires an appropriate scale of v. For example, the mode of the joint likelihood is not invariant to transformations of v, and different conclusions will be drawn depending on the scale of v, chosen when the mode is used for inference about random effect. Toward in this, the novelty of Lee and others in 1996 is to limit the possible joint likelihoods to a given scale of v by resolving the invariance problem. Therefore, equation 7 represents for inference about fixed parameters. We can use the marginal likelihood derived from the functions theta, y, phi by integrating out random effects. Also, equation 7 is a classical Fisher likelihood, and we can obtain the maximum likelihood estimator for theta, maximizing the functions theta, y. For estimating variance components, Peterson and Thompson in 1971 suggest a random effect maximum likelihood approach to improve the estimation properties with reduced bias. Random effect maximum likelihood for linear models can be extended to their GLMs through a more general specifications as conditional likelihoods. Function theta, y with conditions beta hat, where beta hat is the estimator for the mean parameters. By recall the linear mixed model, we have our models with y equals to x beta plus z phi plus error. With v here is follow the normality distributions with mean 0, and our variance is lambda I. Residual follow the normal distributions with the mean 0 and variance psi metric identity I. Towards in this, the marginal likelihood is given by these equations, where our v minus double z transpose lambda plus I c. From the marginal likelihood, we can obtain the maximum likelihood estimators like this. And to the random effect mixed model, estimator equations for variance components is obtained from these equations. The x likelihood is given by the logarithmic functions theta, y phi, and we do summarizations with the log functions theta, y with conditions v, plus log function theta, v, and where n is the number of observations and m is the length of v. Therefore, the joint maximizations for beta and v gives Henderson's mixed model equations, which gives base linear unbiased predictions or BLUP for v and maximum likelihood estimator for the beta. Regarding the deriving sample variance from the random effect maximum likelihood, we can suppose that we have y1, y2 until yn are IID. The observations from the normal distributions with mean mu and variance sigma square, where both parameters are unknown. The maximum likelihood estimator for mu is the sample mean from the mu hat. Whereas direct maximizations of log likelihood give the bias estimator by sigma square hat, and we can consider the REML likelihood as this question. In addition, we can ignoring constant terms. The REML log likelihoods becomes these questions. And we can maximizing the log likelihood, we obtain the random effect maximum likelihood estimator of sigma square hat. Hence, we can see that the RML estimator adjusts for the degree of the freedom. The two estimators will be similar for large N. However, when the number of mean parameters, including the number of parameters included in the mean part of the model, grows with the sample size, the two estimators can be very different. Section 3. Extended Likelihood Principle. To begin with, Birnbaum in the 1962 proved that the classical likelihood functions contains all the information in the observed data about the fixed parameters. In line with this, Bjornstad in 1996 extended this concept and showed that all the information in the data Y for the parameter theta and unobservables phi is in the extended likelihood. This means the inference about the fixed parameters and unobservables. Using the information only in the data, we curse the extended likelihood functions and nothing else. However, these likelihood principles do not show how the information in the data can be retrieved from the likelihood. In the absence of V, the extended likelihood becomes the marginal likelihood. Figures advocate the use of the ML estimations and establish the underlying theory. In the absence of theta, we see that the extended likelihood gives Bayesian posteriors and its use has been advocated by Bayesian statisticians. This gives an insight on how to make inferences in at least these two extreme cases, so that we may develop a procedure which gives identical inferences to that using the marginal likelihoods for the theta, and exploiting the property of the predictive probability, or we call it posterior, for V in these two extreme cases. In the concept of HGLMs, Lee and others in 1996 and 2005 respectively advocate the use of the X likelihood and presents how information in the data where unobservables and parameters can be retrieved from it under the extended likelihood for all the three types of object by theta, V, and Y respectively. At the same time, similarly as for classical likelihood inference, we have a model for the data generation process and corresponding likelihood. Just like the stochastic model, generate an instance of the random quantities V from a probability functions f theta V. With V fixed, generate an instance of the data Y from a probability functions f theta Y with conditions V. The combination stochastic models is given by a product of the f theta V, f theta Y with conditions V. In line with this, the statistical inference we can given by Y, we make the inference about theta by using the marginal likelihood. And given theta, we make the inference about V by using the conditional likelihood by following the equations A. And from the equation A, we can extend its likelihood for unknowns V and theta by given in equations 9, where these conditions. The connections between the two processes is given by equations 10. In the extended likelihood framework, V appears in stochastic models as random instance, but it appears in statistical inference as unknowns. From equations 9 in previous slide, we see that the extended likelihood is the product of two likelihoods, the first likelihood f theta y and the second the conditions likelihood with the functions theta v with conditions y. In likelihood theory, the product of two likelihoods is a way gathering information from the two independent sources of data. You can read more detail in chapter 1 of the book. This is straightforward to note the close connections between the Fisher's likelihood and the X likelihood, because it used the Fisher's likelihood for inference about our theta. For continuous and more detail, Lee and Nelder 1996 proposed the use of the hierarchical likelihood, an extended likelihood limited to the predefined scale of V. Suppose we have two models for the random effects in a linear predictions as eta 1 equals to x beta plus V and eta 2 equals to x beta xp V. Then we have two alternative extended likelihood based on two different scales of random effects following equations 11. And the models of the two likelihoods differ. The questions is which scale of random effect used for statistical inference. We define the strong canonical scale of V such that the random effect V carry no information about the fixed effect theta x as following these questions, where the theta 1 and theta 2 are two sets of theta values, and V hat theta 1 and V hat theta 2 are the modes of the likelihood, theta 1 V and YV, and likelihood theta 2 V and YV respectively. The X likelihood is defined as the extended likelihood having V on a canonical scale. This means that the marginal likelihood gives the same modes estimators about the fixed effect as the X likelihood, so that there is no conflict between the classical likelihood inference and X likelihood inference. For example, in the linear mixed model, V is on canonical scale to beta, which implies the that joint maximizations of H with respect to beta and V gives the maximum likelihood for beta. In XGLN, the X likelihood is defined under a weak canonical scale, where the random effects combine additively with the fixed effect in a linear predictor. From the linear predictor, eta 1 above, we see that likelihood 1, theta V with conditions YV, is the likelihood which gives us a consistent inference framework, following by Lee, Nelder, and Pawitan in 2017. The likelihood 1, theta V, YV, equals to functions theta Y with conditions eta 1, functions theta V, is called a hierarchical likelihood, as the random effect enter linearly in the linear predictors. An important difference between the transforming fixed versus random effects is that a transformation of random effects requires the need to multiply the density functions for the random effects with a Jacobian. In the sense, when V is a discrete, there is no Jacobian involved, so that all standard likelihood are the X likelihood. Subchapter 4, Laplace approximations for integrals. For the linear mixed model, both the margin likelihood and REML likelihood are straightforward to derive, but for most other distributions, the integral for the maximum likelihood has no analytical form. Numerical integrations are infeasible if the number of integrands is the large, and MCMC algorithms are often too slow. As an alternative, use Laplace approximations in the X likelihood approach. Therefore, the first order Laplace approximations for some integrals following like integral exponential function x dx, where the x0 is a global maximum of functions x. For the marginal likelihood, the Laplace approximations around the fifth random effect is following like this, where the v hat is obtained from the mode of the functions theta with the y and v. By applying a Laplace approximations to eliminate random effects together with a quadratic approximations around the beta hat on the RML likelihood, f theta y with conditions beta hat to eliminate fixed effect, And we can get these equations. To eliminate fixed effect, we get like this. To this end, the Laplace approximations for the log marginal likelihood is specified as an adjusted profile X likelihood, or EPHL, by following equations 12, where IV is the information matrix for the random effects. Also, the approximations for the log RML likelihood log f theta y with conditions beta hat can also be expressed as in equations 13, where I, beta, and V is the information matrix for the fixed and random effects. Besides, the estimates of fixed effects and dispersion parameter are computed by maximizing these two likelihoods. 5. Street magicians. Her example is presented to illustrate the fundamental idea of likelihood inference and how it may differ from Bayesian inference. First, a street magician has a small bag with a number of dice. There are two types of dice in the bag, white and blue. The white are number 1 to 6, while the blue have 3 sides with 1 and 3 sides with 2. The magician throws a dice at random from the bag without showing it to you, and rolls the dice. Then he claims that the number is 2. A. Which type of dice would you guess he has rolled? A white or a blue? B. The magician lets you bet on the color of dice. Which odds would you accept? Now, the magicians inform that there are 20 white dice and 10 blue dice in the bag. What's your guess on the color of dice? Which he rolled? Then we can calculate 10 of solutions. The likelihood for a white dice is 1 per 6, and for a blue dice is 1 per 2. Solutions of A, the likelihood for a white dice is 1 per 6, and for a blue dice is 1 per 2. Therefore, as a likelihood is, the maximum likelihood guess is the dice is blue. First, let Y be the number of dice and let big C be a color of dice, and let small c be a realized value of the color of dice. Then, the likelihood ratio is following like this. Py equals to 2 with condition C is blue divided by Py equals to with condition C is white, which is 1 per 2 divided 1 per 6, and the result is 3. Solutions of B. To be able to make probability statements, we need to know the distributions of the two types of dice in the bag. This is unknown, however, which means that for a likelihood is, the odds cannot be computed. A Bayesian would guess the distributions and theory be compute the odds following like this. By controversy is how to determine by P, C, which is blue, and P, C, which is white. And solution of C. The problem can be solved using the probabilistic argument. Here, we also show that both the classical likelihood ratio and the ratio of extended likelihoods can be used to draw the same conclusions. Let C be a realized value of the color of dice such that LC blue equals to PC blue, which is 1 per 3, and LC white, which is the probability of C white, which is 2 per 3. And we can calculating the ratio of extended likelihood is 3 per 2. Thus, the maximum extended likelihood guess is that dice is blue. Furthermore, we can compute the condition likelihood like this, which is the L C blue with conditions Y equals to 2 and L C blue Y2 divided by L Y2, and we can get the results 3 per 5. And for get the L C white and Y2, we can get the result 2 per 5. We call the likelihood C white with conditions Y2 the predictive probability. Following the solutions of C, note that the conditions likelihood L, C blue with conditions Y2 depends upon the likelihood ratio, which is the L, C white divided by L C blue. So, it is invariant with respect to the transformations of data parameterizations. Furthermore, we can get the result 3/2, which is the mode of the conditional likelihood L C with conditions Y2 is the same as the mode of the external likelihood L C with the Y2. In point C, we have an information of probability C, part of the model, while in B, no information is available on probability C, so that we need a guess PC. 6. X likelihood and empirical bias. Inference of random events have important practical use in predictions. A typical example is, for instance, if there are repeated observations on patients' hospital visits, and the lifetime of these patients are to be predicted. This would require a survival analysis including random effects for patients, and the uncertainty in the predictions would include the uncertainty of the fitted random effects. When theta is known, we can make inference about V, functions theta V with conditions Y. However, theta is unknown, so that we may make inference using the theta hat V with conditions Y, with theta hat being the maximum likelihood estimator. This is the so-called EB approach, or empirical bias, which gives consistent estimator for predictive probability, because theta hat is consistent. However, in infinity samples, this approach often has a poor inferential performance because it cannot account for uncertainty caused by estimating theta, especially when the number of observations is low and the number of parameters in theta is large. Such an uncertainty about theta hat is including in functions theta Y, and can be used for inference on random effect, following Lee and Nader in 1996 and 2001. Thus, an important question is how to eliminate the nuisance parameter theta from the predictive probability functions theta V with conditions Y, by using the information on theta in the likelihood function theta Y. And the next slide illustrates the difference using a linear mixed model as an example. First, for a linear mixed model, we have these equations, which is Y equals to X beta plus ZV plus E, which is V following normal distributions with mean 0 and variance lambda I, and E following normal distributions with mean 0 and variance Xi. Therefore, the X likelihood is following like this. When the N is the number of observations and N is the length of V. In a linear mixed model, estimates of both beta and V can be computed by maximizing the X likelihood. The score equations by following derivative H divided by derivative beta, the result should be 0, and derivative H divided by derivative V should be 0. Give Henderson's mixed models equations like this. And the information matrix computed from the second derivative is following like this. The above equations is fitting algorithm of regression model get these results, where the E1 following the normal distributions with the mean 0 and variance Xi, and the residual 2 following normal distributions with mean 0 and variance lambda I. This is called data augmentations method. This is the different from the empirical bias approach by F theta V with conditions Y, where the information matrix 1 per C Z transpose Z plus I 1 per lambda. A more true exposition is found in section 5.4 of Lee, Nader, and Pawitant, showing that the X likelihood gives correct inference. To make predictions of random events, because the future likelihood F theta Y does not involve V, the other component, the predictive probability F theta V with conditions Y, carries all information in the data about the unobsevables. Thus, the predictions of the random event can be made via the empirical bias method, using the estimated predictive probability or posterior, by following P, V with conditions Y equals to functions theta hat with V with condition Y, which is P, V with conditions Y and theta hat, where theta hat is the usual maximum likelihood estimator, following by Carlis and Lewis in 2000s. However, using f theta hat V with conditions Y to make inference about V is naive. And Beyond Stars in 1990 has shown how badly it performs in measuring the true uncertainty in estimating V. Note that maximizations of the X likelihood following like this: H equals to log f theta with the Y conditions V plus log f theta V, and the result is log f theta V with conditions Y plus log f theta Y. The years of empirical bias mode estimators for V without computing f theta V with conditions Y, where equals to functions theta Y V derived by f theta Y. However, the Hessian matrix of second derivatives based upon f theta V conditions Y gives a naive variance estimate for the predictions we had, because it doesn't properly account for the uncertainty caused by estimating theta. That is in f theta Y. The X likelihood considers both components and gives proper estimators for random event and their variance estimator. However, the estimations of the first two moments are not enough for accurate inference of random effect if it is not normal. The perfect example shows that V hat is the neither a consistent estimator of V, nor follows the asymptotic normal distribution. Thus, interval estimations of random event differ from those of fixed effects. Note that the predictive probability functions theta hat V with conditions Y gives an asymptotically correct inference. Thus, it is necessary to have affinity sample adjustments to account for information loss caused by estimating theta. This can be generally done by following Lee and Kim in 2016 by show that equations like this, where zeta theta is the confidence density in chapter 1 of Lee, Nelder and Pawitan 2017. Because the bootstrap distributions gives an estimate of confidence density, we can have the bootstrap method to get the predictive probability by probability V with conditions Y, and the theta 1 star until theta B star are the bootstrap replicates of theta hat. In the complex model, it may not be easy to design the bootstrap scheme, so there is the convenience to generate the bootstrap replicates of theta hat from the asymptotic normal distributions of the theta or the normalized likelihood. Via a simulation studies, Lee and Kim 2016 demonstrates the bootstrap methods provide excellent predictions intervals for future random events, including the predictions of future outcomes in the front. Therefore, we will try to practice open the Adverters Analytics, browse, adjust the data, epilepsy. So this is our data. We have Y, T, B, A, V, patients, and ID. So epilepsy. Epilepsy is a longitudinal data from our clinical trials of 59 epileptics. We have Y, which is seizure counts during 2 weeks periods before each of 4 visits to the clinic. And therefore we have T, which is categorized by 1, new drug, and 0 should be placebo. B, logarithm of the average number of epileptic seizures recorded in the 8-week period preceding the trials. And A, logarithm of age. Therefore, V represents as number of clinic visits. And we have 59 patients with the ID data 236 data. In addition, we have 6 models. Model 1 represents as Poisson generous linear model. Model 2 is the Poissons with the normal SGLM or GL mixed model. Model 4 negative binomials with the gamma SGLM. Model 5 offer dispersed Poissons GLM, and Model 6 offer dispersed Poisson with normal SGLM. And to run scaled regressions, log linear model, choose the response variable y, instructions variable with b and t, selects the n, t, a, v, b, t as the independent variables. Click Run, and this is our model summary. Regarding the p-value of our coefficients, all the variables less than 5%, therefore our variable is significant. And check the model chicken plot and also predictions. To measure our models, see the model summary, which is the residual deviance. At the same time, we will try to analyze our second models, which is Poissons with normal SGLM. Open the albatross, click Random Effect Models, choose Empirical GLM, choose the response variable, y, interactions variable b and t, append, select b, t, a, v, b, t as the independent variables, choose the distributions Poisson. Therefore, table mean represents all for our variables, provides p-value less than alpha 5%, and our variable is significant. See the table likelihood to justify the error for our model. And click the model checking plot to see the scatter plot of our residual and click the predictions. Change the type of mean 11131 and we get our mean predictor. Check the calculators for data. Change the type of arithmetics mean y. And this is our new mean. Therefore, we set the random effects, patience, the distributions for random effects, gamma, and this is the corrections of our random effect model. We get the estimate of our lambda patience, which is -1. Also, if you want to know more details, select the ID for random effects. So we have two random effect here, patience and the ID. The distributions for the random effect 2 should be gamma. Click Run. And we get the estimate for our patience and our ID. In line with this, table means represents that our T, A, V, B, T, the p-value more than 5%, which is this variable is not significant for this model. Nevertheless, change the distribution of mean 1 with the gamma and select the model checking plot. For pulse of random effect 1, and our confidence interval, and see the predictions. So we will use the model for V, delete the random effects, and click run, and we can get the RV with the scale deviance of 230, and this is the intercept of our V. Therefore, select random effect patients. We can change the distributions for random effect, but we set the Gaussian here. Click run. Click model checking plot, scatter plot of our models, intervals, 95% for confidence intervals for random effect, and comparisons model. This is our comparisons model with various of model. But the main distribution is Poisson. From the table likelihood, we can measure the error for our 6 models with the corrections AIC. And the best model is model 4, which is the lowest corrections AIC. And the best model is negative binomial with the gamma SGLM.